analysis, we basically measured it using Urdhva simulation only. Now looking into it, we got a dynamic power of 3 milliwatts. Now this is very low, and this is only the dynamic power of the core logic and signals, not the actual board itself. Now the actual board uses around like 130 milliwatts. Now that is static power. Now dynamic power is what they measured in the reference paper. Now this might be, would say, closer to actually 30 or 40 if you actually implemented it in the board. Like for example, if you are showing this logic with the blinking of LED or any other part of the board, that will use some amount of power. So this dynamic power may change according to the logic here. Now as for the number of LUTs utilized here, as you can see, we utilized a very less amount of lookup tables, that is around 34 for our model, but it could be, you could say, higher if we utilize structural modeling instead of, you could say, those fast carry adder chains in the addition area. For reference and the conventional multipliers, they may use around like 80 to 90 or even 100 LUTs or even more than, depending on their designs. We didn't exactly see their numbers, so we just named them as 18 LUTs and 18 slices of LUTs, so maybe actually more and a higher number of LUTs. Looking to here, this is the screenshot from Urdhva regarding how much power, how much wattage each part of the process is taking. As I conclude, I would say we achieved a good delay of 7.6 to 3 nanoseconds, which is 11% improvement over the reference design, which is very nice, I would say. And comparing the efficiency, I think it would be lower even when implemented in a real board. The reference paper did it in a basis 3 board, so I would recommend trying in that. As for future scope, we could increase the number of bits, which is basically bit width scaling. We did 8-bit, could increase it to around even a 64-bit architecture, as this board can handle it, even though it's pipelining could be done to further reduce latency. And quantum computing is also pretty important because these reversible gates have zero information loss, which is basically a key component of quantum computing. So we can utilize this in that also. And these are the references we utilized.